Sure. Oh, yes, of course. True color, true color, true color. Now, where is that? Oh, true tone, that's it. Ooh, it's exciting. The only thing more complicated than I/O is screen sharing.
Yeah, that's good. Yeah, Anil, the floor is yours.
Thanks very much. All right. So I'm really glad to be here because the first question I had when thinking about what to talk about here was, are I/O libraries really an interesting research area? Because they sound pretty boring when you look at them at face value. But then when you step back and look at the evolution of these libraries over the decades, it actually gets pretty interesting because ultimately, computers aren't very much use if they don't do I/O. We do a whole bunch of computation, but if you don't shift the data to the right places, then there's not much utility in that computation. So making sure that we keep up with whatever we need to do to feed our CPUs and our GPUs with I/O is extremely important. And if you step back a little bit, I've realized that over the last kind of 30 years, I've been actually doing the same things again and again. And I thought I would highlight some of those things in order to give you some guidelines about perhaps the direction we should go in when it comes to managing our runtimes. So back in 1996, when I started using OCaml, life was pretty simple. It was single core machines, they were spinning hard drives, and Unix mattered a lot. Like the idea that we would have a single standard called POSIX remained true and important and relevant. And then this technology called Zen came on that I worked on, where we had this idea of virtualizing machines. I'll talk more about that. And then by about 2004, multi-core became a thing. SSDs and flash drives emerged. Linux and Windows started to dominate versus Solaris and a lot of the other operating systems that were around at the time. And then, a few years later, started working on a technology called Docker, which started bringing containerization to the masses and working on different and interesting ways of doing systems virtualization. And then, meanwhile, of course, the world had been moving on, and hardware became really diverse. So, and today, my development machine has 768 cores. It's got 4 terabytes of RAM. I work on exabytes of data for environmental science, so processing the world's satellite data in order to come up with insights to help with the world's biodiversity. And what this boils down to is that the amount of data has increased, the number of cores have increased, the heterogeneity of how we deploy our services has massively increased, including the deployment of really exciting browser-based technologies, and there's GPUs everywhere with machine learning workloads. So where we are right now is that although we're orders of magnitude bigger, the way that we have to approach how we process this data has got to change. And for our old friend POSIX, who here knows what POSIX is? You've almost all programmed in POSIX at some point, right? And I realized that POSIX was my rubric, my idol when I was doing systems programming. When I was an OpenBSD developer, I would make sure that we were POSIX compliant. And then slowly, as technologies arrived, they began to wrap POSIX, things like Zen and Docker, and progressively, there's been an extension in the way that we process our software, and now POSIX is just an illusion. It's just a memory of something that once was, and it's holding us back. And so I'm going to try to make the case here for why, when you do virtual machine design at any level, you should not think about POSIX first, and you should move forward into new APIs and treat POSIX as very much a slow compatibility layer that is not a first-class citizen here as well. Does anyone? I see a few people shaking their heads. Interesting enough, actually. So let's see if you're convinced by the end of it. So what I'm going to talk to you about over the next few minutes is that, first of all, I'll make this case for why it's really, really important that we step away from POSIX as the way that we interface with the outside world from virtual machines, mainly because of the prevalence of shared memory parallelism. And then in the second bit of the talk, I'll talk about what some of these post-POSIX interfaces are. And just to give me a sense of how much you know, how many people here have used IO-Uring or, okay, we've got 1 or 2, okay, so 1 and 3. What about Grand Central Dispatch? Any iOS developers in the audience? So actually, the same people are putting your hands up. How many of you are also OS developers or Okay, we got two of the same ones. But generally speaking, most of the audience have not used these next generation technologies. And I'll explain what they are and give you a sense of how they fit into the stack. And then, back in OCaml, in my home turf, we've been having a go at just trying to build in support for this as a first-class effort, and I'll explain the work in progress that we've been doing towards that, using lots of fancy new features in the OCaml 5 tool stack, mainly effect handlers. But first, let's look at the case for a post-POSIX system. And as a runtime developer, you're always in a slightly awkward middle ground because you're sitting between the applications and a certain kind of hardware stack, right? And it's really hard to keep everyone satisfied. You have to satisfy the application developers who won't tell you what they're doing. And then you have to satisfy the environments you run on. And so it turns out that this story is repeated all the way through the hardware stack. And when deploying applications, it's very useful to know what that stack actually is. And the first thing that happens is that we almost always have a kernel in the way. And this kernel is ever growing. So Linux has grown to over 45 million lines of code over the last 30 years or so. It began on a single floppy disk. And the reason it's so complex is that it acts as a middleware for the world's hardware and effectively the world's software as well. And it provides high-level services like storage and networking. And it has to schedule them and provide isolation. But when you look at the kernel, it really is a kernel of two halves. The bottom half of the kernel deals with the low-level things, like how do you interface with hardware? And this is the majority of the complexity in Linux, because the reason it is so dominant is that anytime there's some new hardware, the first thing that a hardware manufacturer does is to write drivers for Linux. The second thing is to document it. Maybe the 10th thing. But really, it's all about making sure that interrupt handling and memory and CPUs are dispatched correctly. And hardware has become really diverse if you think about just what's happened in the last 30 years. And there are tens of thousands of device drivers and hundreds of classes of drivers in there. But they essentially make sure that they can take something that's coming from some I/O memory and steer it towards eventually a CPU at some point. And the way that they do this is that they use ring buffers. And ring buffers are a block of memory where you've got a producer and a consumer, and one side pushes something onto the shared memory buffer, and the other side consumes it. And at the lowest level, this happens in hardware usually. So a network card, for example, it ultimately boils down to some shared memory somewhere and something keeping track and synchronizing of the shared memory buffer. You might have one queue in the NIC that is pushing packets that are received, and then we're reading them off, and then it goes through a long bit of the kernel, and then vice versa, when I'm writing, I write to some hardware buffer. Maybe I have a bunch of copies, maybe it's zero copy, but fundamentally, this is a synchronization mechanism that we have with the hardware as well, and then a bunch of configuration as well. So shared memory buffers are what we have at the lowest level of our computers usually. Then, the second bit of the kernel is isolation. It's trying to figure out, how do I take this low-level stuff and then have a bunch of hostile processes that are multi-tenant and try to make sure that we can make these things compatible and work together. And so the kernel's job is to deprivilege something called user space and then to provide an interface and an API towards all of these tens of thousands of device drivers. And it does this, this privilege context switch through a system call interface. And the system call interface is pretty monolithic. It is simultaneously saying, give me a privilege switch so that you no longer trust me, and you can look at my data, and then you can access the privileged hardware. And also, it's an instruction to do something as well. And it's a fairly synchronous process. So the system call interface is quite a request response with synchrony built in, and it's the primary API that POSIX specifies in order to do things with your computer. So any process will always have a syscall interface as the only way to do side effects. So without that, you've got a process that is effectively functionally pure because it's got no way of having the results materialize elsewhere on real hardware. And then we finally get to the runtime, the bit at the bottom of the stack that has to go through all these layers. And this layer is usually uses something called libc, which is a C-based compatibility layer over syscalls. So this is the quote-unquote portability layer. And this abstracts the very low-level part of the syscalls into a C-based API. So one that is not assembly-based, one that is more or less architecture independent and can make these calls. And this is where standards like POSIX have historically specified what you should do when it comes to making function calls. So this standard works across kernels and it works across architectures. And this is then what our runtimes usually link against in order to talk to the world. But you can see here that the stack is pretty big, right? When you're looking at this already. And we're only about 2004 here. And the problem here is that as our machines get more and more multi-core, we have to, in our runtimes, figure out how to use all these resources, even though they're multi-core and NVMe and Flash and so on. And it's really difficult to do this without some cooperation. And the problem is all these layers tend to fight each other at a scheduling level. So multiplex scheduling is when you have two schedulers trying to schedule the same resources, and then they inevitably fight, and they're just not as effective as having one scheduler. And so it's quite hard to use all of this. And so obviously the answer is to add another level of abstraction. So because it's so hard, we thought, let's just carve up the machine into smaller pieces, and then now we can schedule these smaller pieces, and we don't have to schedule across those, and that's what hypervisors are. And so that's what we use in the cloud. But effectively, we've now got yet another layer between us and the thing that's actually doing the work, the hardware. And there's tens of billions of virtual machines in the cloud with this. But the way that the hypervisors work is very relevant to this argument, because what a hypervisor does is that it tries to give you safe isolation to real hardware without having a performance impact. And the way it does this is by patching the kernel to fool it into thinking it's running into real hardware, or using some hardware instructions, a combination of both. And then it has a mechanism by which it can give you the virtual device drivers to the kernel, which are then used for everything downstream. So you don't have to make any changes to your runtimes or your applications. And how do these things work? Well, they essentially work through a sequence of rings. And these rings are mapped either to the real hardware, so known as a backend driver, or into the front end, which is the kernel that has been virtualized. And then ultimately, we've got something where requests are pushed into a front-end driver. And then the hypervisor then looks at the requests. It just gives them a quick once-over to make sure they're in the right region. And then it sends it to the real hardware, which itself has rings. And so it can be quite efficient. And a well-designed hypervisor, like Zen, can make sure that it uses hardware support for this checking to be really fast. So usually using page tables or other mechanisms. And what this boils down to is that these rings are actually quite well aligned because they're both mapping onto the same underlying kind of constructs. And once you set up the channel, your data path is very, very quick. You're just flipping memory around, and it's like you've set up a highway for these things to go down. So it works okay. And then they're still fighting each other, and so you have to be a little bit careful about how you make these things kind of work together. But then, unfortunately, because of that fighting, virtualization was quite heavyweight by about 2014. And so even though we had a few billion virtual machines, there was no real genuine sharing going on. And so Docker came along and containerization. Docker kind of glued together a lot of pieces in the technologies that made containerization, but it's essentially another layer of virtualization, but at the namespace level. So when you try to open a resource, instead of having a full virtual machine and kernel, in things like Docker, you can share the kernel, and then the names of the resources you try to access are shimmed. So if I try to access, for example, /root/Alice in this case, then it will actually, inside a namespace, I can just make /Alice my root, and I'll never be able to escape. But once you open that resource, it's just like a normal kernel resource. And again, it goes through a bit of a fast path of POSIX and so on. So containerization was a useful way to provide lightweight name-based multiplexing while sharing the kernel. And it also then uses shared memory in order to make various transitions as it goes through its data path. So if you're a runtime developer, you're designing a new virtual machine or an existing one, there's quite a tower of cards here. It's kind of a miracle sometimes that computers work. But all of these things are where you have to go through in order to just send a packet or read a block from disk. It's just most of the time it's hidden away. Now, we have a bunch of shared memory rings here. And this is how computers stay reasonably fast and how we can partition up resources. Until POSIX where you've got a bunch of syscalls, and it's like you're driving along at 150 hours on a motorbike on a very safe path, and suddenly you've got to make some control turns. You've got to synchronize, you've got to stop, you've got to have privilege checks, and this is fundamentally almost impossible to parallelize. And so if you are working in this stack of things and you care about performance and you care about getting the maximum bang for buck out of your very expensive kind of modern multi-core hardware, this is the bottleneck that defines all of the bottlenecks when it comes to any kind of I/O in your systems. And so it's really, really hard to kind of make that work. And reflecting this fact, there has now been a concerted move across all operating systems and browsers and everything else to basically bypass POSIX. But we haven't quite realized it yet as well. So for those who are shaking your heads, are you now reasonably convinced that POSIX is a bad thing when you see the stack? Okay, I see a couple of nods. It's surprising how much you can forget the layers of software and hardware kind of behind every simple operation that you do. But really, the rubric is that if you've got a bit of memory, then you can do very fast tricks with memory to make them go across multiple layers of abstraction without any real performance impact. There is some, but not a huge amount, and you can go at kind of near wire speed. As soon as you take page faults or any kind of other control operations, things get really slow. And so what are these post-POSIX systems that we want to think about when it comes to developing them? So let's have a look at what that is now. So we now know it's OK to just start designing things without POSIX. But let's understand what it is first. So the essence of any kind of system call in an operating system is that you first of all, you decide what operation you want to do. You pack it up into a C function call, which then becomes a bunch of arguments that is hardware specific. It's either goes in the register for a hardware instruction, or it can be packed into various other kind of instruction formats. But the kernel then doesn't trust anything about what you've given it. If you give it some memory, then the kernel will pause the process. It'll either copy memory into its kernel space, so user space can no longer modify it sneakily through a parallel process. It then executes something, and then it returns. So for every single call that you do, there's quite a lot of work that happens. And so this is an S-trace. So this is the result of showing you what happens at a syscall level whenever, in this case, I'm just doing a simple read and write. So you can see for this process ID, the fact that we're reading some value, we've then got some threading-based synchronization, because in order to let the user space process continue, you need some way to make that synchronous thing asynchronous. So this is now blocking. You've got poll, which is a somewhat legendary instruction that almost all of you who've used POSIX have used, but has subtle variations. It's quite hard to scale. You have to pass in all the FDs statically, and then you're polling for the result. A whole bunch of thread synchronization thing happens, and then you're finally writing a result. And this is for one resource. And so you can imagine that if you're doing things at scale, so a modern machine, my machine has 4 terabytes of RAM, so it can handle millions and millions of processes. This synchronicity is a bit of a death knell to doing anything performant. So what does it look like if you step away from this? If you have a fun Sunday morning where you're thinking about life, it's always worth reading the Linux kernel. Because this is what Stephen Dolan has taught me. Because it turns out that there's loads of system calls beyond POSIX where just by flicking through the manual pages and the header files, you can actually discover a whole world of new interfaces, some of which were bad ideas, but you can still learn from them. And Uring, which is the newest kind of game in town, TBD if it's a good or a bad idea, but it's definitely an idea. And what it does is that it gives you rings, just like we've seen with the Zen and the network cards. And the basic idea here is that we have 2 rings, a submission queue for requests and a completion queue. And these are just normal memory pages mapped in at a configurable size. And what happens is that applications submit a request from user space just by writing something to the shared memory ring. And you have a producer and consumer pointer that decides where you're going to write based on an index. And critically, when you write the request, your runtime can decide some arbitrary user data that we'll then come back to later on. And the set of operations you write are just C-based operations, where in this example here, there's a full link, if you look at my slides later on, which shows you the kind of operations you write. You can read and write and poll and send messages and things. It's very similar to the syscall interface, but not entirely complete. And then you submit these, and you submit a whole bunch of these things, and then the kernel goes off and does the work, and asynchronously at some future point, and out of order, writes CQEs in, which are the responses to this thing. And the way that you tie the completion queues to the submission queues is that user data, that pointer that you passed in, is maintained by the kernel and tracked, and it just gives you that back. And then it's your job to dispatch everything, read the responses from the completion queue, interpret the result, and then pass it back to your mutator as well. So the CQE here, the struct, is very simple. It's just the user data, the result, and a bunch of flags about some metadata about the request, which I'll come to later on. So the essence of this is that the amount of work that you do when you send a request from a syscall level is algorithmically better. So this is for a bunch of parallel requests, and the only thing I need to do into the kernel from a systrace perspective is call one thing called IO ring enter that is a signal that there is something in the ring. Later on, if people are just pushing things to the ring, I don't even need to do this syscall, because the kernel will just note that there's unconsumed requests, and it will just continue to poll, and it will stop polling at some point, and then whenever I see that the ring is empty, I just give it a prod to wake up again, and that's it. So we've gone from this rather busy thing per process to something that's quite relaxing. You're just saying, here's a ring, I'm going to keep putting stuff on there, and I'm just going to tell you whenever you need to wake up and do something about it. And then you can, at your own time, look at the completion queue, and hopefully not too lazily, because you'll drop events if you take too long, but you can consume it at your own pace as well. So we've decoupled the synchronicity in the kernel now. And crucially, we've also decoupled the security context switches and all the other things that happen as well. That's all part of the U-ring protocol. So U-ring has a ton of features to further increase performance, and these map onto the kind of things that you have in hardware. So things like link requests, you can do multiple writes, and they act as memory barriers, so you can stop. They can go out of order across the barriers, very similar to memory things. You can even steer requests towards particular cores, so that you can control where the memory heads to. So in a NUMA architecture, you can control your latencies as well, and a bunch of ways to make repeated operations cacheable. So fixed buffers mean that you don't have to register the same memory buffers all over again, and you can further minimize the amount of thrashing that happens. But there's a but. In order to do this, it's extremely hard to retrofit an existing application to use this POSIX to take full advantage of this API, because it's so much richer. You've got the ability to submit batches, they're linked, you're essentially submitting a data flow graph to the kernel, and then asynchronously reading it back as well. So again, POSIX will hold us back if we do too much of that. And you also have to make sure that your buffer management is top quality. If your buffer management is a little bit fast and loose, as has been on occasion the case in my code in old school OCaml, then things go very rapidly wrong because of the amount of concurrency here as well. So you could get away with it in POSIX sometimes, but not really here as well. You're trying to minimize copying and maximize throughput. And so the interesting thing about U-ring is how similar it is to further downstream hardware interfaces. And the same kind of questions come up in operating systems and in runtimes and in the way that we manage U-ring. You need to figure out how big should this ring be, what do you do when it's full, how many threads and cores do we map these rings to? These are new questions when it comes to I/O management in Linux, but they're very old questions when it comes to questions of what runtimes do and what operating systems do as well. So I'm hopeful that this part of it is something that's really quite manageable. Then there's a slight downside. Although there's similarities to the way that it works in other bits, there's one kind of slight problem, and that is it became a really good way to make money. And so whenever you've got these synchronous calls to the kernel, Linux historically is actually not synchronous internally. It's got a lot of state that means that it can block internally whenever it comes to doing things. So suddenly, we've got a user space API where we can submit bazillions of asynchronous requests to Linux, but internally, the kernel is now forced to do a bit of a control inversion and then store those in some kernel resources. And this is anathema to the kernel, because the kernel hates having to allocate memory. Because if it runs out of memory, the only thing it can do is to start destroying user space processes, and the killer comes along. And this usually kills the biggest allocator of memory, which is usually the runtime, right? So the big managed runtime that's trying to get a whole bunch of other work done as well. So this is a disaster if this happens. And so Uring has exposed a bunch of architectural deficiencies in the Linux kernel. And so there's an enormous kind of hygiene cleaning going on that might take the rest of the decade, but it's important that it happens. And so Google has actually suspended, before you all go off and find more vulnerabilities, it suspended its vulnerability notifications because there was just too much being paid out. You can see here that the IO ring was the majority of CVs in the kernel in 2023. It's still happening. More features are being added, and more things are being found. But there's an expectation that the architecture of the kernel knows what it needs to do next as well. So just bear in mind before we switch to this thing, it's not a complete panacea, but this is the direction of travel that I'm arguing for. The surprising news is that there is a kernel that is actually quite asynchronous internally and has a rather beautiful setup. And unexpectedly, it is Dave Cutler's NT kernel that is still at its heart in Windows, actually quite an amazing asynchronous I/O heart. Where Windows kind of falls over is it's kind of the opposite of Linux. The user space interfaces are appalling to use. There's just many, many variations. But the kernel is one of the most beautiful kernels I've ever worked on. And this means that finally Windows can have its shining spotlight in the sunny day, because Windows can actually have a Uring-style API where it can handle the asynchronicity effortlessly in the kernel, and then therefore not have all of these CVs. It's got security issues for other reasons, but not for this particular I/O interface. And so Windows, although being Microsoft, they couldn't quite resist giving it loads of names. So there's a separate set of APIs for file system management called IO Ring, which has a very similar interface to IO Uring, and then for networks called RIO. And overall, the overall term is called overlapping I/O. The idea that you can essentially submit these requests and have it overlap for some reasonable amount of time. So this is good news, right? Because in our major operating systems, Windows and Linux, we've got very similar looking shared ring APIs. So we're good. We're good to go, right? Security, apart from security. The problem is our old friend macOS. So macOS also has wanted to expose this concurrency for a long time. Ever since the shift from PowerPC to Intel, macOS has been going more and more multi-core. And it's got a very complex mechanism of queues where the kernel and the user space can declare their concurrency requirements, and the kernel can then independently scale its kernel-side resources or its user space resources through a mechanism known as libdispatch or Grand Central Dispatch. If you've done any kind of iOS programming or macOS programming using these native APIs, you will have seen these interfaces. They permeate all the way through the stack. But the slight hitch is that they don't expose enough information. They still only expose these queuing abstractions and not the shared memory rings. So it means that there is a scheduler hidden in macOS that will be fighting with the runtime, and you can't make these harmonious as well. But we'll come back to macOS. Apple's always a little bit awkward when it comes to building these APIs, but you can, in theory, get the performance out of it as well. And then after this, we've got our friends. I've lost my keyboard entirely. Oh, it's crashed. Oh, this is exciting. Speaking of macOS, I didn't mean to badmouth you, Apple. I'm really sorry. Ooh, that went horribly wrong. And then, of course, we've got new backends like WASI, where you're trying to build these runtime interfaces in, but you have to decide how to dispatch the high-level APIs to these backends. And what is interesting about WASI that we'll see when we come to our language design is that it is firmly free of POSIX in the front end, because the basic WebAssembly interfaces in the browser essentially had no system interfaces. And then we've seen a whole bunch of innovation in things like WASI, the component model. We've had lots of talks here at the ICP and Splash about this. But crucially, the emerging model is that we talk to the outside world through capabilities. That is, we declare what we want to do, we have some state that can be passed around, and then that can be used in order to access a resource. So from the backend's perspective, it's actually surprisingly easy to look at all the active capabilities and schedule the kind of things you want to do as well. And so then the WASM runtimes can decide, well, we can bypass POSIX because the applications never expect to have POSIX. And so this is a path by which we can imagine getting rid of the need for this historical 40-year-old compatibility layer and actually implementing high-performance applications. But the one golden rule to keep in mind is that at some point you do want to expose shared memory so that you don't try to build a competing scheduler that will then destroy the performance advantages that you have this way around. So we've seen that in almost all the major operating systems, there's hints of these new upcoming things. And then there's a bunch of new backends in different operating systems, of which I've only touched on a few. Doing a survey while preparing for this, I was really, really pleased to see just how much is going on. Even in the BSDs, they're not quite dead yet. They're definitely hurting a little bit now. But there's new interfaces for security management. OpenBSD has got things for sandboxing and stuff, which is, in my view, better than most things in Linux. Then we've got innovations in the bare metal side, where you can do bare metal programming using unikernels and hypervisor level management. And so every single system that I've seen has essentially moved past POSIX now as well. And so the challenge becomes not so much how do we maintain POSIX compatibility as the first thing that we do, but really about how do we go back to exploiting these things, making them ergonomic to program with, and then using that as the basis for the way that we deploy future systems, instead of the first thing that we do to say that we're going to build an amazing runtime with the greatest GC and out-of-time compiler and cherry sandboxing, and then completely throttling its potential by using these old APIs as well. And so what I'm going to talk about now is give you a brief view about how we're looking at this in OCaml. How many people here have used OCaml before? Just to give me a sense of who knows the syntax. Who's got no idea what's going on with OCaml? Amazing. There was no one for the record, for the streaming record. Oh, I'm really pleased. So the first slide I showed you had lots of tool stacks, and I've built a lot of OCaml code in production for Zen and for Docker, and these have been a long-running kind of system. And the way that these have historically worked, and the way that I've programmed using OCaml 4 and previously, is that you build a system where, in order to do a portable thing that could be deployed in all kinds of systems contexts, you want to abstract the operating system as much as possible. And in order to abstract the OS as much as possible, what I do is I first of all use OCaml functors, which are parameterized modules for those coming from Haskell. And they give us a bit of portability by letting us abstract across a console interface or a notion of time, so I can use different timer sources. And then in order to begin a function, I pass in an existential that tells me that I have a capability to use this hardware. In this case, the C is a console first-class module that corresponds to this this first-class module here. And then in order to then block, I use monadic concurrency, which is a user space library that just says, run this thing after this thing, using LWT for those familiar with it as well. So this has been a very classic way to program, and I've very happily written quite a few hundreds of lines of code that work this way. But then there's a whole bunch of problems with that, because ideally it is a bit verbose when it comes down to it. And so the thing that we've done new is to develop a new feature in OCaml 5 where we can make this happen. We can just begin something called EIO main, and then I can run using a direct style control flow, and I've actually removed a huge amount of the boilerplate. No more functors. Capabilities are passed in through a mechanism that is very subtyping friendly, and then it's direct style blocking. The semicolon is back in OCaml. And we can use imperative affordances, because it's really nice having for loops in OCaml, right? And having to rewrite everything in a recursive style using monads just got a bit tedious after a while, and lots of syntax extensions came up. So the direction of travel here in OCaml 5 is to say, well, we can rewrite a bunch of code. We can use subtyping and a new feature, which I'll explain next, in order to make this happen. How many of you here have played with OCaml 5's effects? So, oh, interesting. So while almost all of you knew what OCaml was, OCaml 5 has had a new feature, which I'll explain next. Only about a quarter of you have seen this one before. And what this lets us do is that it lets us, in user space, define resumable continuations. And reasonable continuations mean that reasonable exceptions which have a continuation in order to do the resumption. And it lets us write code like this, where I can define a function called fork, which can block internally, and then I can do another fork, and then I can even do message passing between these two functions through this exchange thing, and no monadic concurrency is required. So we can write in user space, using these new effect handlers, all of the logic required to implement this particular thing. And this is an example from the OCaml 5 manual. So if you want to play with this yourself, I highly encourage just going to the manual and reading the examples that Casey Sivaramakrishnan wrote for that. And how it looks is this, to give you a quick sketch. First of all, you write down the name of the effect, and we have an extensible GADT for all of the effects. So in this case, we define two new effects, one called fork, which takes a function, and another one called yield, which just stops. And then we define convenience functions here just to perform the effects. So at this point, this fork will go off and raise this effect, and the effect has to be handled somewhere. So the handler is quite fun. So in this case, we built a very trivial fiber system where we have a run function. And notice here, again, the lack of any monads. And we define an exchanger, which is just where we're going to store our message passing buffer. Then we can enqueue things by putting them in a normal queue. Except here, now we have something called continue, which can resume a continuation that's passed in. And where does this continuation come from? Well, this comes from the effect handlers. So whenever you spawn something, you can then get a result from the function as normal, at which point we finish the fiber. You can get an exception, at which point you just raise the exception and you dequeue it. So I haven't shown us re-raising the exception, but that's probably what you would do. But we can also now pattern match into something called an effect. And what the effect does is that it like an exception, it has the exception value, but it also comes with a continuation that lets you resume the function at the point that the exception was raised. And continuations are one shot, so you must either discontinue them, it will be a memory leak if you don't, and you can only resume them once. Or there'll be a dynamic exception raised for that. And this means that it can be very, very fast. So they're almost as fast as raising an exception, a little bit more stack keeping, but not much more. And this is enough for us to then build a fiber stack in which you can run this nice direct style code that we saw here, and in user space, define the scheduler that you're trying to aim for as well. And this is a secret for how we can support all of these new I/O backends. And so the thing we learned in about 20 years of OCaml coding is that there's loads of really cool things about OCaml, right? It doesn't force you to do things. It's got a strict execution model. It's got run loops that you can customize. It's the perfect language for systems programming in many ways. Except that handling I/O was really painful because you have all these monads, you have lots of heap allocation, you lose your backtraces, and after a while, debugging that really becomes a drag. And so what we're trying to do here with this new modern I/O library is to help us to match the impedances from these systems where we've got all these shared memory protocols and make them run as fast and as ergonomically while maintaining the programming affordances that we need. So I want my backtraces, right? When I'm looking at a production backtrace from Docker from a very, very grumpy customer. And the way this works is that you essentially have to think about I/O in the modern runtime as being a DSL from the mutator that is interpreted by the backend. And so if you think about, at a very high level, a mutator in a runtime is waiting for I/O. So it's got a data dependency graph of I/O it needs. And then on the other side, you've got a bunch of I/O being produced by some other side, and that's also got its own data dependency graphs. You're trying to match these graphs. And the faster you can make these graphs more bipartite, then the more you can just proceed and make progress. And the more you have to rearrange the graph, the slower you get, because that's just time that you're not processing the graph. And so in EIO, we have a bunch of high-level functions that try to, as declaratively as possible, manage I/O without specifying exactly how to manage it. So in the old days, if I wanted to copy a buffer, I might just create a buffer, copy, read a magic number in here, and then output it to stdout. And now what we do is in EIO, we say, well, give me a flow.copy and define input and output flows instead. And then the backend can decide how to spawn the fibers, to manage all the shared memory queues, because it's got a notion of user-level concurrency that has been defined by the application. And therefore, then the OCaml runtime can go off and decide how to keep its shared memory buffers full, which then propagate all the way down the stack as well. it's good at a high level. It has been really interesting in EIO, experimenting with writing front ends and back ends to all of the different pieces. A lot of this work has been done by Patrick Ferris and Thomas Leonard, where initially I just set the challenge out saying, well, let's just build an IO ring back end, because that was the most obvious one. And then we had the POSIX backend as well, but it's kind of a second-class citizen. You have to use POSIX sometimes because IO ring isn't quite complete yet. And then we've ended up with macOS where it just doesn't work because of all of the guaranteed dispatch. So we're still trying to figure out exactly how to map the runtime to the fact that the kernel might decide to move CPUs and so on. It's possible, but it's going to be a bit slow and messy. But it'll be stable. And then we have Windows where it looks near perfect because of the amazing amount of asynchrony there. And Windows has always been painful because its POSIX backend isn't really POSIX at all. And there's lots of translation layers to make that work over the last kind of 20 years in OCaml, heroically maintained by David Alsop. But now with these new backends, David is getting excited again by the prospect of writing IO code because it could potentially be the best backend for OCaml anywhere. And BSC is kind of being left behind at the moment because it's still got to use a POSIX backend, but POSIX does still work. It'll just be a bit slow. And then we have exciting new backends. In JavaScript, you can choose to use a higher level API. And then in unikernel backends, you can decide exactly how to dispatch the I/O because you have full control in the backend as well about how you manage I/O. So all we do is that in our low-level interfaces, we expose each of these individual libraries that give you the greatest, lowest level non-scheduling interface towards these low-level interfaces, and then we provide high-level interfaces that are more declarative and managed using the effect system in order to do dispatch as well as possible to the most native API available in the operating system. And only if that doesn't work does it fall back to POSIX, and it'll operate more slowly. So just to give you a sense of what it looks like, it's super fun binding shared memory protocols, super dangerous and super fun. We have type-safe bindings to IO ring in Linux where you can use nice OCaml combinators to do the lifetime management. So here, I'm just managing the heap. One of the really nice things about the U-ring bindings is that user data I mentioned that you push onto the queue into the kernel is the continuation of the fiber. And so the only thing that the runtime has to do, apart from a tiny bit of bookkeeping, is just to basically jump to that continuation, and it's in the OCaml runtime. So the amount of bookwork from some I/O event completing in the kernel to being in the mutator is extraordinarily small. And this was not the case with using historical backends like select and poll, where, as you saw in the syscall trace, you have to do a lot of work in the runtime. So it's refreshingly small and simple. And then, while there is a certain amount of dynamic lifetime management, there are further advanced extensions to OCaml coming up now, such as OCaml. You would have seen that in the Jane Street booth, where we have the prospect of doing more lifetime management at the type level. And so, therefore, the direction of travel of this is one of safety eventually, even if there's some dynamicity in it right now. And then the high-level interface is looking very much like WASI and like WebAssembly, where we have capabilities exposed as the default programming model for everything we do in EIO. So you can do things like you have a standard environment that is using object types, which are really syntactically convenient in OCaml, even if they're much maligned. I'm a big fan. Because you can ergonomically subtype them to say that I just need these parts of my environment in order to make progress. So stood-in, for example, is just an object type of a source where it only has a stood-in function, and then you can have all kinds of interfaces exposed using this subtyping-friendly interface as well. And then just to give you a hint, also you should go off and look at the EIO documentation to get a full sense of it. It's actually really nice when doing systems programming because the type gives you a lot of information about the resources you need to access. It seems kind of obvious, but we just haven't had that in the way that we program all of this time. Right? When you look at a function now, I can see that my certificate management here requires a network interface in order to do something. It doesn't say what. And you can, in user space, further refine these to do more application-specific capabilities. Whenever we're reading things from disk, we always take in an environment. And this environment then allows the system to use the best sandboxing-friendly APIs available. And then this is all enough for us to proceed and then dispatch them to the back end, where POSIX simply does not have the right security primitives to make these things work well, but we know that Linux does, and so therefore we use the best-of-breed APIs for that platform. The ultimate goal is that when you look at a trace of operations from your application to your runtime, to your kernel, to your hardware, it should be as if you've handwritten it, right? If you knew exactly what you were doing and you knew exactly what the stack was, how can we get as close to that as possible and as aligned as possible without any kind of magical programming? And this is obviously not perfect yet, but it's getting us in that direction because we can unlock the ability to use modern kind of I/O backends, and then we can focus our attention next on memory management and lifetimes and all the other things that we need to also worry about as well. So I've given you a bit of a whirlwind tour into sort of where we've been going with all these backends, and I just wanted to recap some of the high-level points for you as designers and implementers and users of managed runtimes. The first thing is that try to make your managed runtime not block. Just don't stop if you want to go fast. Seems like a good training trick. And so recognize that there are shared memory channels all the way through the stack. Use them and make them easier to share. So isolation is easy to do in an operating system. You just turn the thing off. Safe sharing is really what makes operating system design really hard, because you have to define what safe means and what sharing means and how long it's going to happen. And so this is really the core API challenge behind, I think, exposing these new APIs. And just remember that POSIX, if you ever see it, will basically slow you down, but it's still around causing trouble because it's still the back end. So just treat it as the second thing that you work on and not the first thing, and then it'll help you kind of focus your design minds on exactly how things are going to work. And so while this is true for Linux and Windows, macOS remains awkward. And so I think an active research area that would be really interesting is trying to figure out exactly what lies between the shared queue model of macOS and the lower level shared memory rings. It should entirely be possible, for example, to build an MN queuing concurrent model on top of the lower level APIs, but to my knowledge, it hasn't been done yet. So libdispatch and Swift have been ported to Linux, but not in the kind of high-performer way I would have expected, presumably because it's not a very popular deployment target. But there exists the ability to do these things, or to do them within a managed runtime as well. And if you want to experiment with these things, EIO is by no means a perfect library, but it's what I use day-to-day in OCaml programming today for doing my day-to-day work, so on planetary computing. So I process petabytes of data using this thing. It hasn't crashed. It's been pretty ergonomic. I've been a happy user because it exposes primitives for zero-copy memory. It's got higher-level interfaces that don't take advantage of all of the backends yet, but as we write more code, we're getting familiar with where to plug in these optimization passes, and the use of capabilities has been really refreshing. Like, it's caught genuine bugs in code where the wrong file system directory is being opened, that kind of stuff. And it just gives you another level of hygiene, which we should all be using in the modern day as well. So it's definitely very much a Wild West. I hope I've convinced you that I/O research can be fun. You have to have a problem that demands this, and so I encourage you to find problems where you've got lots of data and latency requirements and interactivity, and then just dive in and experiment with some of these backends and start sharing information and knowledge about how to pull that off as well. So with that, I'll conclude, and I'd be happy to take any questions you might have. Thank you.
Yeah, thank you for the great talk. So we still have 10 minutes for questions. So if you have questions, please make a queue in front of the microphone.
So great talk, thank you. So it seems like IOU ring is kind of a response to two things being expensive. One is system calls being expensive because of privilege changing, and also threads being expensive. Yep. So I'm wondering, so you didn't mention Go at all, and Go's concurrency model. I'm curious if there was something about that that you could think about also in this space.
That's a great question. I've never had good experiences with the Go concurrency model after doing a lot of Go in Docker, mainly because we found that we had to avoid the first-class concurrency primitives in order to get high performance in Go. So you generally don't want to use lots of Go routines if you want high performance Go. And so we ended up in systems code of essentially de-Go routining the code, and ending up with surprisingly low-level code to make that work. So I view Go routines a lot like using standard ML style synchronization, because it couples up synchronization with communication. And I do think an essential point of all of these shared memory rings is that you want to decouple synchronization from the act of communication. And so we're not coupling them in our EIO libraries. But historically in OCaml, we've done the same thing as well when using standard shared memory channels. What I haven't seen is if Go has an IOU ring backend, and I'd love to investigate that more after your question. Does anyone know if Go has a I/O U-ring backend? Any Go programmers there? One thing I have seen is that it's surprisingly hard to retrofit I/O U-ring though. So Rust's Talk I/O took a long time to have a U-ring backend because again, if they've coupled just enough in their previous API, it's very hard to figure out where to insert the scheduler. And that's what we have with effects in OCaml is that we have a place to shim a scheduler in that we can control at an application level as well. So perhaps that's the key difference. If Go gets user-defined effects, it might be easier to write the Go synchronization routines in Go itself.
Yeah, just a final comment on that. It also seems like you have to be a Go expert to be in the Go runtime. Like it's not like you can go and modify the Go runtime easily as a non-core developer.
That's right. A lot of this was inspired by, I think, Casey Silverman Christian. He interned with Simon PJ, the Simon & Simons in Haskell 2013 or something, and he wrote a user space Haskell scheduler for their really fancy runtime then. And that's really what inspired all this work because we're like, well, why don't we do this in OCaml? We have to make it multi-core, so we might as well write these things as well. So, and then happily, the I/O backends all kind of accelerated, so everything's converged at the right time. But you're right. The EIO backend is subtle and quick to anger, so it's not something you want to casually modify, but it's something you can modify without having to recompile your language. I think that's important.
Thanks.
Thanks, man.
Hi, Anil. Thanks for a very stimulating talk. I have a comment that I think I can make into a question at the end. The comment is that POSIX is my semicolon. So in the middle of your talk, you said, oh, no, OCaml actually, it's nice to have semicolons. We have these affordances that we like, right? And that's the way I think about POSIX, right? So you spend a lot of the talk basically saying POSIX bad, you should hate POSIX. I mean, you didn't quite say that. But actually, nothing in POSIX is opposed to having shared memory interfaces on the side, right? So I suppose, how do you reconcile these two attitudes? I feel like I could go on about how, more and more asynchrony isn't necessarily a globally good thing, right? Yeah. So I don't know if you... I think I finished my comment without actually asking a question. How do you reconcile those two ways of looking at the world?
Stephen, I will reconcile that by crossing the line and giving you a giant POSIX hug. Because you're completely right. When booting an operating system, when doing interactive debugging, there's all kinds of reasons why you want to do that, right? So if you think about a lifetime of a computer, there's a boot process, there's a configuration process, and there's a go leave it for 10 years process where you just want to do things. The boot process, the configuration process, all of that should be, a nice, simple, synchronous API. When you want to make it go fast, you then want to leave it alone, and that's where you want to activate all this stuff in. So POSIX is a wonderful place to do configuration and mess around with things. And so is a browser as well, in a different way. And so if we phase these things right, then everything will find its time and place. And I'm definitely not saying get rid of POSIX, but I am saying if the steady state purpose of a runtime is to process exabytes of data potentially over the lifetime of the process, then you should design first for that data flow, and then everything else should come around that and make it ergonomic. And that's where I see POSIX fitting into all this as well. But I'm a huge fan of extending POSIX, and I wish there was a way to reconcile these two things. One of the concerns here is that we don't have a POSIX-like process that helps to bring these things together. So the Windows U-ring and the I/O U-ring backends are subtly different in terms of their metadata. They expose a lot of the kernel. We've seen the security issues. So if anyone's motivated, and I'm looking directly at you now, it's actually a great time to try to define the semantics of what POSIX 2026 looks like. That is a departure from that. Maybe give it a new name. And in fact, if anyone wants to chat about that here, it feels like a good place to discuss this over drinks. Thanks. So thank you for that comment.
Hi, wonderful talk. I've also had some, I've also tried out EIO and I found it pretty ergonomic.
Oh, good.
But I also wanted to ask about, so here in this case, you decided to say, okay, I/O U-ring is something that is worth kind of keeping. So we're going to build like a abstraction over it, and we're going to expose it to more, I guess, more general audience who doesn't maybe know as much about like the low-level API. But there's also things like ePOL, which never really took off. So how do we as language implementers know which features are worth supporting abstractions for, and which features we can kind of skip out on?
It's a great question. So there is, to quickly recount the history of FT synchronization, you've got POL, PPOL, KQ, ePOL, U-ring. There's quite a few of them. They're all different. Right, so they all, Select obviously, I forgot my old friend Select. They're all different because some are edge triggered, some are level triggered, some have different scalability, some have dynamically sized in terms of the number of FTs you have. So you really have to size them to your environment. it's very hard to build a runtime where you don't know what the deployments are going to be. And I think one of the points of Uring is that it's actually quite feature extensible. So if you know that you're going to be running on an embedded device, you're probably going to go for a simple polling style interface, because that's ultimately, you don't need to have a million FDs. The problem really arises when you don't know where your runtime is going to run, right? And that's often been the case with things like Docker and Zen and things where people just deploy them in unexpected ways. So one of the things I've been thinking about in Uring is that you can actually write a shared memory proxy in user space that can translate to all of these other APIs pretty well. So one thing that might be worth investigating in runtime is to say, make it shared memory first, and then you dispatch by processing in an internal thread in your runtime to one of these kind of backends, if that's the only thing available. That's kind of effectively what EIO does, but in a slightly roundabout way. But you can also then make this a first-class citizen, right? You can translate between language runtimes if you wanted to. Because shared memory, it's a network protocol that can't go over the network, but it can go across cores and across different parts of the machine. So if I had to build a multi-language interoperability story, I would do it over Uring now, because that would cover the full set of RPCs you would need to do across the runtimes, and then put an internal translation in, for example, to Go or anything else as well. So it doesn't quite answer your question, but it's really about how much extensibility you want. And I think that's when you want to look at these new things. I'd be very cautious about making Uring the default runtime only, given the, you really need a modern Linux today, and this is really a direction of travel. So you have to get familiar with all the APIs, unfortunately, right now. But if it come back in 5 years, it might be a different case. These things take time to migrate.
Sounds great. Thank you.
Thank you.
Hello, thank you for the talk. Very, very nice, very
I'm glad.
interesting. I'm Polydor Spratikakis from University of Crete. We are using a combination of memory map and I/O to basically use remote memory or storage devices as memory, as parts of the memory hierarchy. How are these faster ways working with memory map? Can you still use memory map as your safety net and then use as I/O to accelerate?
Right.
Like,
it's a great question. So the question is essentially, once you have memory, how do you manage that memory? So the short story is that this tower continues up and it continues down. And so in the hardware, there's a bunch of synchronization built in for different types of memory. And usually this happens at the hardware level, right? So it does cache coherent synchronization. But then when you have different types of memory, like network memory or GPU memory, you've got a bunch of protocols which are increasingly exposed to user space in order to manage them. So this is particularly true for GPUs, where most of modern systems programming is tensor networking, right, to GPUs. And so you've got things like NVLink and ways to manage all these cards. There's probably around 15 to 20 kind of widely deployed APIs at different levels of stack, all the way from InfiniBand and RDMA to various forms of persistent memory, which have now been canceled, like Octane, and then all of the GPU and FPGA interconnects as well. So it is an open question saying, we could in theory write protocols for each of these low-level drivers and do exactly what I described here. I haven't done that yet. I'm not quite masochist enough, I think. You have to have a very specific problem to make that happen. But a lot of this does happen in operating systems and hypervisors today. So if I look at the Zen evolution today, there's specific kind of backends to do with memory mapping metadata, which is where you shove all this. So normally a page is readable or writable or executable. Now there's many, many more things that tell you about the coherence of the memory. Is it write through, where it'll go, the source and destination, and also generally what the alignment requirements are, for.
So they do work together.
It does work, but it's an extremely manual process right now, and we're really hampered by the fact that NVIDIA doesn't export. It doesn't have a good open source story at all. Right, so the documentation joke I made is really quite true. We just have to reverse engineering all of these pieces.
Well, I was thinking of storage, not GPU.
So storage is really interesting. There's a bunch of new products where the flash chips can be programmed directly, and they have got their own kind of flash local memory, and they have FPGAs on them as well. And so
the page table will follow the Uring.
No, they do not follow the Uring thing, because those tend to have more of a they have a tiny operating system essentially running on there. So you've got a little bit of memory, you've got the flash chips, you've got a protocol to write to the flash chips, and you've got a tiny amount of FPGA local memory to make that work. So think of it as a different operating system. And then you've got thousands of them. And then your job with Uring is to dispatch the right parts of the storage so you've got to build a file system or some abstraction on top of that as well. So you need to know what it is you're building. So if you're building a vector store, for example, with lots of sparseness, then you define the hash function in user space, and then you dispatch the function. So in theory, you could build that with EIO. We just haven't, but it'll be a really fun exercise to do that as well.
Thanks.
Thanks.
Thanks so much.